Share screen. Okay. So can you see
Yes.
these notes on the screen?
Yes.
Okay. So what got me involved in this is a few months ago, there was a new biography of von Neumann published by a man named Bhattacharya. And I'm in the process of writing a review of this biography for the American Math Society notices. And I thought, which makes perfect sense, I believe, that if you're writing a biography, if you're writing about von Neumann, at least, and you're a mathematician, you should know something about what von Neumann actually did, by which I mean, read a paper or two. And there is a beautiful essay by Freeman Dyson called A Walk Through Johnny von Neumann's Garden. Freeman Dyson describes von Neumann's fundamental contributions to mathematics, physics, computer science, and then he adds a sort of a remark. In another corner of the garden, there was a little flower all by itself, a short paper that solves a problem raised by the Polish mathematician Hugo Steinhaus. Johnny solved the Steinhaus problem quickly and never returned to it. The theorem that he proved is counterintuitive, and the proof is astonishing. So I thought, if Dyson wrote that, I should actually read this paper. And that's what I'm going to talk about today. So Steinhaus's problem is to partition an interval, that is an interval in the real, a finite interval in the real line, into countably infinitely many pairwise disjoint sets that are congruent in the set that each set is a translate of a fixed set A. So I don't know if Steinhaus ever published the problem. As far as I know, the problem was first stated in 1921 in a paper by Stefan Mazurkiewicz, who says, if you don't like the French, one can decompose the line into infinitely many, countably infinitely many non-measurable sets, pairwise disjoint. Steinhaus remarked that we don't know if it's possible to solve the problem of an analogous decomposition of a segment, for example, the unit interval. So the Steinhaus question is, can you take this closed unit interval and partition it into countably infinitely many pairwise disjoint sets that are congruent in the sense that each is a translate of the other? So that's the Steinhaus problem. And this is the problem that von Neumann solved. I should point out, if you take the interval from 0 to 1, then this may have been another problem of Steinhaus. Can you actually decompose it into a finite number greater than 1, 2 or more pairwise disjoint pieces that are congruent to each other? And that problem is solved, but it was unsolved for a very long time. You see, if you take a half open interval, the solution is trivial. But if you take the closed interval or the open interval, it's not at all trivial. But Steinhaus's problem was to partition an interval into countably infinitely many congruent pieces, pairwise disjoint congruent pieces. Now you can ask, what is an interval? And there are 4 kinds of intervals. You can have an open interval, you can have a half open, half closed interval, or a closed interval. For partitions into a finite number of pieces, the half open, half closed intervals have trivial positive solutions. For the open and the closed intervals, it's not so obvious. So, and what von Neumann did is he solved the Steinhaus problem for all 4 types of intervals, right? It doesn't matter which type of interval you take. So for every interval I, von Neumann proved the existence of a set A and a sequence, a countably infinite sequence of real numbers, such that this set of translates of A, these sets are, so they're congruent because each is a translate of each other, are pairwise disjoint, and the interval is the disjoint union of this set of translates. And so it follows, for example, that the set A is necessarily a non-measurable set, because if A were measurable, if it had measure 0, the union would have 0 measure. If it had positive measure, the union would have infinite measure. So A has to be a non-measurable set. And so I want to describe von Neumann's proof and also extend it from intervals in R to parallel pipets in Rn.
Mel, is the construction effective?
Exactly the same size, just up to limit.
Is it effective? First of all, so the answer is no. I'll say something about that in a second, but I don't think there is any effective construction of a non-measurable set.
Without the axiom of choice, I mean, you can have a axiom system where every set is measurable.
Right, I'm about to mention that.
And okay.
Okay.
I don't understand what the set A is doing here, because instead of saying of a bunch of men that they're all the same height as each other, I could say they're all the same height as Mel Nathanson, but Mel Nathanson is superfluous in that case.
Well, so you can state this result in several equivalent ways. One is that, exactly as I stated it, there's a fixed set A and a countably infinite number of translates of A, such that the translates are pairwise disjoint and their union is the interval. Alternatively, you can say you can partition the interval I into countably infinitely many pieces, and each piece is a translate of every other piece.
Yeah.
I mean, it's exactly the same thing. Okay. Now, one can coincidentally restate this problem in the language of additive number theory. So in general, if you have an additive semigroup and take subsets A, B, and C, we know the sum set A plus B is everything that is the sum of an element of A and an element of B. And the set C is the sum of the sets A and B if A plus B equals C. We say that C is the direct sum of A and B if A plus B equals C, and every element in C has a unique representation as the sum of an element in A and an element in B. And so you have the following sort of trivial identity. Suppose C is A plus B, it's a sum set. So you can write that as the sum of translates of A. It's the union of A plus little b over all elements of the set B. And you can also write it as the sum as the union of translates of B. It's all elements of A. It's B translated by all elements of A. So these sets are all congruent to each other. They're all congruent to A. And these sets are all congruent to each other. This is useful from the following point of view. If C is the union of countably infinitely many congruent sets, so let's say that B is a countably infinite set. So here A plus B is a union of countably infinitely many sets. But if and only if C is also the union of an arbitrary number of sets, which are all congruent to some set B, which is countably infinite, right? So you can either say that C is the sum of countably many uncountable sets, or the union of uncountably many countable sets. And von Neumann, without using this language, makes exactly this observation, and it is one of the key parts of his proof. So we get in equivalent forms of Steinhaus's problem. The original problem is to prove that every interval was the union of a countably infinite number of pairwise disjoint congruent sets. Alternatively, prove that every interval is the union of uncountably many pairwise disjoint sets, each of which is congruent to a fixed countably infinite set. I mean, it's just, all right. And this is something that I don't need yet, so skip that. Now, one of the things I learned after spending a lot of time trying to understand von Neumann's paper and being completely impressed by how out of nowhere he has this idea of using the axiom of choice to construct a set, which is basically a set of coset representatives of a certain group. And then I somehow looked up what may be the first construction, in quotes, construction of a non-measurable set, which was due to Vitali. So Lebesgue was doing his work on measure theory at the very beginning of the 20th century. I mean, his earliest papers, the papers that I saw, were from 1902, 1903. And in 1905, Giuseppe Vitali proved that there exist sets of real numbers that are not measurable with respect to any normalized translation invariant measures on omega. So omega is just a sigma algebra that contains on the line that contains all the intervals. So it contains all the Borel sets. And normalized means that the measure of an interval is the length of an interval, of the interval. And translation invariant means that if you take a set A and translate it by B, the measure of A plus B is the same as the measure of A. So with respect to any normalized translation invariant measure, Vitali proved that there exists a non-measurable set. And in his proof, he uses the axiom of choice to construct a set of coset representatives of a quotient group. And von Neumann uses this idea in his proof. So just very quickly, I want to sort of sketch what Vitali did. And, you know, in retrospect, it's very simple, but, you know, you have to be brilliant to come up with a simple idea. So, so you take the rational numbers, that's a subgroup of the real numbers as an additive group. You take the quotient group. And the set Q, the rationals, you know, are dense in R. And so if you translate Q, that is, if you take any coset X plus Q, that's also dense in R. So in particular, every coset intersects the unit interval. So by the axiom of choice, the only reason I'm saying the axiom of choice is, as Moshe said, it turns out that the existence of non-measurable sets is essentially equivalent to the axiom of choice. So using the axiom of choice, and you construct what is called a Vitali set by choosing an element from the intersection of each coset of in R mod Q with the unit interval. So this Vitali set is a subset that contains exactly one element, V of X, from each coset X plus Q. Well, so yeah, it's a subset of 0, 1 that contains exactly one element from each coset X plus Q. And Vitali's theorem is that every Vitali set fails to be measurable with respect to every normalized invariant measure. So I'm sure, I assume, that sometime 100 years ago or so, when I was learning measure theory, it probably included Vitali's proof. But I couldn't find it in Halmosh's book on measure theory, for example. So there's a very quick proof of Vitali's theorem. If you look at all the rationals in the interval from -1 to 1, that's, I mean, the rationals are countably infinite. So this intersection is countably infinite. And I can enumerate the elements, Q1, Q2, Q3, and so forth. Okay, so I have this enumeration of the rationals between -1 and +1. And I take a Vitali set, that is a set of coset representatives in the unit interval. And the first thing is to show that if I translate the Vitali set by one of these rational numbers, I get infinitely many pairwise disjoint sets. So let's see, why is that? So if you have V plus Qi and V plus Qj that have a point in common, then they're real numbers X and Y, such that V of X plus Qi, that's something in this set, is equal to V of Y plus Qj, something in this set. So V of X minus V of Y is Qj minus Qi, that's rational. And if the difference is rational, then these two numbers belong to the same coset, so they have to be equal, because we only have one coset representative from each coset. So these translated sets v plus q sub I gives us a countably infinite set of pairwise disjoint and obviously congruent subsets of the reals. So now we do some baby arithmetic. If v is in the Vitali set, it's between 0 and 1. If q sub I is in this set, it's between -1 and +1. So if you add them, v of x plus qi is some number between -1 and 2. So if you take the union of all of these sets, v plus qi, they're all contained in the interval from -1 to 2. So this union is contained in the interval from -1 to 2. Right? On the other hand, if you take any real number x in the interval and its coset representative v of x, so we have 2 points between 0 and 1. So the difference is between -1 and +1. And moreover, x minus v of x, well, the two, x and v of x is a coset representative of x. They belong to the same coset. So the difference is rational. So x minus v of x is equal to some rational number. And we know that it's between -1 and +1. So x minus v of x is equal to one of these numbers, q sub I. So x is v of x plus qi. This should be a lowercase I, is in here, which means what was x? X was any number in the unit interval, right? So the whole unit interval was contained in this union. So what I have is this union contains the unit interval, and it's contained in an interval of length at most 3. So if mu were a normalized translation invariant measure, and if the set V were measurable, then each of these sets has the same measure, mu of V. And 1, which is the measure of the unit interval, because the measure is normalized, is less than or equal to this. These are pairwise disjoint sets, which is this, which is less than or equal to 3. And this inequality is impossible, because if V had measure 0, you'd have 0 is between 1 and 3. And if V had measure positive, this would be infinite. So that is Vitali's proof, right? I mean, it's beautiful, right? And so that, I assume, was one of the key things that von Neumann knew when he was trying to solve his Steinhaus problem. By the way, as Moshe mentioned, Robert Solovey constructed a model of Zermelo-Frankel set theory without the axiom of choice, but with something called an inaccessible cardinal. Has to have an inaccessible, uncountable cardinal. And in this model, every set of real numbers is Lebesgue measurable. So in this sense, the axiom of choice is equivalent to the existence of non-Lebesgue measurable sets. An inaccessible cardinal just means a cardinal number that you can't get from smaller cardinals by adding, multiplying, or exponentiating. So for example, Aleph naught is an inaccessible cardinal, because you can't get Aleph naught by adding, multiplying, or exponentiating finite cardinals, right? So that's Solovey's theorem. Okay. So now I want to sketch the von Neumann's proof, his solution of Steinhaus's problem. And so von Neumann used Vitali's idea of applying the axiom of choice to the intersection of an interval I with the cosets of some countably infinite dense subgroup of R. Now, the rational numbers, the set of rational numbers is a countably infinite dense subgroup of R. Von Neumann constructs a different countably infinite dense subgroup. So the key to the proof is the following construction of a countably infinite set B of Q independent real numbers. That is, the set B of real numbers is linearly independent over the rationals. And among other things, this set B will have exactly 2 accumulation points, right? 2 points that are limits of sequences of other elements of the set. And the way it's done in general is the following. Suppose I take real numbers beta naught, beta 1, and delta. Delta is positive. So beta naught plus delta is less than beta 1 minus delta, right? So delta is less than the difference than beta 1 minus. Anyway, beta naught is less than beta 1, and you choose delta such that beta naught plus delta is less than beta 1 minus delta. So there exists a countably infinite set of real numbers such that the set B, this countably infinite set, is linearly independent over Q. And the numbers satisfy the following. First of all, B naught is between beta 0 and beta 0 plus delta. And for every even number, B naught, B2, B4, like they're all between B naught and beta, between B naught and beta naught plus delta. And the limit of the sequence of the even terms of the B's is B naught. Similarly, I choose B1 between beta 1 minus delta and beta 1. And all the other odd terms in this set are going to be strictly less than B1 and bigger than beta 1 minus delta. And the limit of these odd terms will be B1. Okay. So I want to construct such a set. And there's an extremely simple way to do it if you're clever. I mean, you know, after the fact, everything is clear, but to think it up is not so obvious. So this is essentially what von Neumann did. He said, take any set sequence of numbers, countably infinite set of real numbers that are linearly independent over Q. So, for example, if you take theta to be pi or e or any transcendental real number, then the set of powers of theta, 1 theta, theta, this is linearly independent over Q. That's what transcendental means. It means that the theta doesn't solve any algebraic equation. Actually, all von Neumann did was just take the powers of E, but again, you can take any transcendental number. All you need to know is that there is such a set. So these are Q independent over the rationals. And if you take any sequence whatsoever of non-zero rational numbers and you multiply the terms of this sequence by this sequence, so you look at Q0, C0, Q1, C1, Q2, C, this new set will also be independent over Q because the Q's are rational, no matter what rational numbers you choose. So, right. So how do we choose the rational numbers? So I want a number B naught between beta naught and beta naught plus delta. So you just find some rational Q naught. So Q naught times C naught falls in that interval. And you just find some rational Q1 such that Q1 C1 falls in this upper interval, right? And just to make it easy, suppose you have some number delta prime such that B naught plus delta prime is between B naught and B naught plus delta. And similarly, B1 minus delta prime. And I just multiply the numbers in this sequence of C's by appropriate rationals. So each B2n satisfies this kind of inequality. And each of the odd numbers satisfies this inequality. And all I've done is multiplied the C's by rationals. So my B sequence is Q independent. And just the way from looking at this inequality, you see that the even numbers in the sequence converge to B naught and the odd numbers in the sequence converge to B1. That's the whole proof, okay? And von Neumann actually does this only in the following special case, which is what he needs. So this is his construction, really. If you take any epsilon greater than 0, there's a countably infinite set of real numbers that are linearly independent over Q. The even numbers are between -2 epsilon and minus epsilon, so they're negative. The odd numbers are between epsilon and 2 epsilon, and the evens converge down to B naught, and the odds converge up to B1. So we take that set B. So that's just a set of numbers. And now we take the subgroup G that is generated by the sequence of B's. So that means all integral linear combinations of the B's. So B is countable, so this group is countable. And they teach you in beginning number theory that if you take any irrational number theta, its multiples are dense mod 1, which is equivalent to the statement, essentially, that if you take any irrational number theta, then the numbers of the form m plus n theta are dense on the real line. So this so this subgroup G is not only countably infinite, but it is also dense in R. Okay. Yeah, that's all that says. Okay. All right, now, so this is von Neumann's theorem. Every finite interval is the union of countably infinitely many pairwise disjoint congruent sets. And again, by finite interval, I mean finite interval, any one of the 4 types of intervals, open, closed, half open, half closed, and so forth. Okay. So take a finite interval. So that C0 be the inf and C1 the sup of the interval. So C0 and C1 may or may not be contained in I, it doesn't matter. And the length of the interval in any case is C1 minus C0. And choose an epsilon that is less than positive epsilon, which is less than C1 minus C0 over 8. It just turns out to be convenient. And for this epsilon, I take this set B I constructed on the previous slide. So this is a set of numbers with exactly 2 accumulation points. One is B0, which is between minus 2 epsilon and minus epsilon. The other, which is positive, is between epsilon and 2 epsilon. And I let G, or G of epsilon, be the countably infinite dense subgroup that this set B generates, right? And again, if you have a dense subgroup and you translate it, a dense subset, and you translate it, you get another dense subset. So every coset of this subgroup G is also countably infinite and dense. And in particular, it follows that every coset intersects the interval I. All right. So using the axiom of choice, I only keep saying this because, first of all, back in the beginning of the 20th century, people like to point out when they were using the axiom of choice. So Vitali and von Neumann always emphasize the fact that they're using the axiom of choice at this point. We take a set V, which will be coset representatives of the group R mod G. In fact, yeah, I don't even have to take them in the interval I. I just take V to be any set of coset representatives of the reals modulo of this subgroup. So for every X in R, there's an element, a unique element V, such that V is an X plus G. And it's obviously uncountable because I'm taking a union of countable sets and getting an uncountable set. That doesn't really matter. So now, okay. So here is like a key point. For every V in this set of coset representatives, I can write my interval I as V plus J, or I should have written this J sub V. So JV is just, so J is just I translated by minus V, right? So J is just another interval of exactly the same length. And if I look at I intersect the coset V plus J, that's I is V plus J sub V. It's this intersection, which is V plus the intersection of this interval with G. And the cosets R minus R mod G partition R. So I have that I, it's the, so the cosets partition the line. So if I look at the intersection of the cosets with I, the union over all the cosets is I. And I only need to take each coset once, so I can just take the union of I intersected with the coset V plus G, where V is in this set of coset representatives. And I can write I plus V intersect J is just V plus J sub V intersect G. It's just, so my set I is a union of translates by V of an interval of the same length as I intersected with G. And okay, so I just really want to emphasize this. This is like the key observation. So my I is a union of these sets, and these sets are pairwise disjoint. And it's a translate of this set I, which is the intersection of some interval with my subgroup G. Right? That's what we have. Now, suppose that for every interval J of length, I write B minus I, but this is the length of I. Suppose I can write G intersect J in the form A plus B for some set A. So what this means is that then for every V, there's a set A sub V, so that JV intersect G is some set plus this set B. And remember, B is this countably infinite set I constructed. It depends on epsilon. And let A be this set, V plus A sub V. Take AV, translate it by V, take the union of all these things. So I is equal to this. J intersect G is this sum, which I can write like this, which is this. And these sets are disjoint, so this is really a direct sum decomposition. So I is A direct sum with B. I is the union of uncountably many, but doesn't matter, some number of translates of this countably infinite set B. And that's exactly what I said was all I needed to do, or von Neumann did, to solve the Steinhaus problem. So the problem reduces to showing that if you take any interval J of this fixed length, whatever it is, B minus A or C1 minus C naught, that J intersect G can be decomposed into the sum of a set A, sum A plus B. Right? That's what Steinhaus's problem reduces to. So they're stated here again. So Steinhaus's problem comes down to this: prove that for every interval J and every epsilon, such that 8 epsilon is between 0 and the length of J, or epsilon is less than the length of J over 8, there's a set A such that J intersect G is A plus B, where G, well, B is the set with the two accumulation points, and G is the subgroup that the set B generates. Now, okay. So we haven't done anything hard yet, and I'm not sure that there's anything that is so hard in the proof, but after it's been done. But in order to prove this, it's going to be a kind of a proof by induction. You see that G is countable, right? G is a subgroup generated by a countably infinite set. So the intersection of J and G is going to be some countably infinite set. This is a countably infinite set. Okay. So if you have a countably infinite set, you can often do things by induction. And that's what it's going to reduce to. So the key part of the proof is buried in this lemma. So the lemma says the following: if you have a finite interval J, C naught is the inf and C1 is the sup, and if you and you take any x in the open interval from C naught to C1 intersected with G, all right? And you choose an epsilon between 0 and the length of j over 8, right? 8 epsilon is this. And you let B be that sequence you construct from the epsilon with the 2 accumulation points. So this is what the lemma says. You have to sort of think about this perhaps a tiny bit. If you take k real numbers such that, so this is this number x. X is something in this interval intersected with G. So suppose I take k translates of B and X is not in any one of them. So X is not in this union. So then one can say two things are possible. There are infinitely many numbers A such that X is in some translate of B by A, and that whole translate is contained in J intersect G on the one hand. And on the other, this translate of B is disjoint from all of these translates. All right. So I have K translates of B. It doesn't contain some element X, which is in this set I'm interested in. And I can find a whole translate of B that is disjoint from all of these sets and contains X. So, I actually have here, and hopefully in a day or two, I will just post this on archive or send it to anyone who's interested, the proof of this, because this proof takes a tiny bit of work. So what we're going to show is that this condition, that there holds for infinitely many A. So the first thing is to show there are infinitely many numbers A, such that the translate A plus B is completely contained in this and contains X. But of course, some of these translates might intersect one of these sets AI plus B. But I want to show that, in fact, there are infinitely many numbers A for which A plus B, in fact, does not intersect any one of these sets. So first, we're going to prove that this condition, equation 5, holds for infinitely many A. And second, that if we add the additional condition that A plus B is disjoint from all of these translates, that excludes only finitely many A's for which this condition is satisfied. And since this holds for infinitely many A's, if you throw out any finite number, there's still infinitely many left. So, yeah, maybe I'll just skip the proof. I mean, proofs I don't like proofs. And, yeah. So make believe that I proved that. All right. I mean, that's the only maybe hard part of the proof, but technical things in talks don't make a lot of sense. So how do you finish von Neumann's proof given that fact? So let me just go back to this lemma and explain what's going to happen. So I want to show that this whole interval I want to show this whole interval is a union of disjoint translates of this set B. So suppose I have, this is countable, right? Because G is countable. So there are only countably many numbers in this set. So suppose I have AI plus B. These are subsets of this interval, a finite number of them. And not everything is in there, of course. So suppose I take a number X, which is in here, but not in this union. So I want to take another translate. I want to show there's another translate of B, which contains X, is contained in this intersection, and is disjoint from all these other sets. Well, this lemma says I can do that. That basically is the whole sort of proof by induction. Take this union, find the smallest in this enumeration of this countably infinite set, find the one with the smallest index, which doesn't appear in this finite union, And then you can find a translate of B that contains the X and it's disjoint from these. So we add it to the collection. And you do this countably infinitely many times and you've covered the set. Wow. That's von Neumann's proof, modulo the hard part. Yeah, that's really all I need to say about that. By the way, you can now extend the Steinhaus problem to parallel pipeds because every parallel piped is a product of intervals, open, closed, or half open, half closed. So we know that every interval is the union of countably infinitely many pairwise disjoint congruent sets. So by the sort of purely additive number theoretical lemma I mentioned earlier, if you have a direct sum of, if a set is a direct sum of two other sets, if you take the product of those sets, you get another direct sum. That's exactly all you need to know to extend the Steinhaus problem to parallel pipets. Now, in geometry, this has led to, as is always the case, an infinite literature on what are called M decompositions. So in general, if you have a group G that acts on a set X, we say that subsets A and A prime are G equivalent or G congruent or congruent with respect to the group and denoted A prime squiggles A. If sigma of A equals A prime for some motion, some transformation in the group. So if Y is a subset of X and G is acting on X, you let M be a finite or infinite cardinal. What is called an M decomposition of Y is a partition of Y into M, should be boldface, M, pairwise disjoint subsets. So where these sets A sub J are all congruent to each other. So this is an M decomposition. So for example, the group Q acts on R by translation, X goes to X plus B. And for every positive integer M, this is an M decomposition of the half closed, half open interval. As I mentioned at the very beginning of the talk, for a long time, it was an open problem to determine if either the open interval or the closed interval had an M decomposition for every integer or some integer M greater than or equal to 2. So this went back again to about the beginning of the 20th century. And in 1951, someone named Gustin proved that such finite decompositions do not exist. Let me just make one last remark. So Freeman Dyson obviously loved this paper of von Neumann, but the paper elicited some curious comments. So in a paper in the 1950s that extended von Neumann's result to M decompositions of an interval for any cardinal number A between Aleph naught and 2 to the Aleph naught. Of course, there may not be any, right? Or at least depends on what model of set theory you're using. But Michalski wrote, the idea of his proof is the same as von Neumann's, but his proof is simplified. And then Stan Wigan, who wrote a survey paper on the subject, also repeated Michalski's assertion that he gave a simplified proof. For me, I found Michalski's proof very complicated, much harder than von Neumann's. So maybe this is just a question of taste. Now, Paul Hamosh, who had been von Neumann's assistant at the Institute for Advanced Study long ago, he did not share Dyson's enthusiasm for this paper of von Neumann. He wrote in a survey, the question of Steinhaus's problem is of a technical gymnastic kind, and von Neumann's positive answer uses the set theoretic and epsilontic trickery appropriate to this domain, which is obviously a put down. Nonetheless, Hamos concludes a survey of von Neumann's contributions to measure and ergodic theory as follows. In quantity, these contributions amount roughly to 1/10 of von Neumann's scientific publications. As to their quality, it seems safe to say that if von Neumann had never done anything else, they would have been sufficient to guarantee him mathematical immortality. This is just the proof of the density theorem. And yeah, and here are references for anyone who might be interested. And that is all I am going to say. So I thank you for your attention.
Mel,
Yes,
are you posting this on archive, or if not, would you email me a copy of it?
so the answer is probably yes to both questions. But given the fact that I forgot to say I was meeting in person at the Graduate Center today, I would encourage you to send me an email to remind me that I should send you a copy.
I will. I'm doing it now. Thanks, Mel.
Okay. Good. We're done. Comments? Oh, yes. Ari, do you have a question?
Yeah, I would just want to have a remark. It reminded me when I took measure theory, I asked the professor built a non-measurable set. I asked him a question that he didn't know to answer on the at the moment. What is the external measure of this set?
Yes.
But instead, I will think about it, and I'll tell you hopefully next time. But if it comes to the von Neumann's construction, I assume that the external measure of the set must be 0.
No. The exterior, the interior measure is zero, but the exterior measure is strictly positive.
It's strictly positive, but
Yeah.
you add up a countable, which is infinite number of positive numbers, which
Yeah, but it's not
doesn't
the
add.
measure.
Oh, I see the measure. Oh, it is strictly positive.
There's like interior measure and exterior measure, right?
Yeah.
Inner measure, outer measure. The inner measure is 0. The outer measure, I believe, I'm sure is strictly positive.
Strictly positive?
Yes. But it's not countably additive, so it doesn't contradict anything about the finiteness of the interval you're covering.
Yeah, okay. Oh, and the internal measure
Zero.
measure is 0?
Yeah.
Yeah,
I guess
okay.
that shows it's non-measurable.
Sorry?
I guess that shows that the set cannot be measurable.
Oh, no, it's definitely not measurable.
Yeah.
Yeah, you mentioned it, yeah.
Yeah.
No, so this can be a good example for a class that you teach, that the outer measure and the inner measure are distinct.
Yeah. But the same is true for the Vitali set, which is much easier to work with. That has
Yeah.
inner measure 0 and outer measure positive.
Yeah, but I'm today far away from measure theory. Yeah. It was a required course back in my days as an undergraduate to take measure theory, and computer science was part of the mathematics, and the computer scientists made a rebellion and a strike that they don't want to take measure theory. Yeah, this was in the old days, in the 1970. Yeah.
Before computer science was a discipline.
It was before it was a discipline. Yeah.
Henrik, did you have a question? Or Guy?
Yeah,
I raised my hand by mistake.
Oh, okay.
I have tons of questions, but you wouldn't like to listen. Another time.
Okay,
Yeah.
whenever.
Did we discuss Yitang Zhang's newest paper in the schmooze session?
No,
so David
Yeah.
Ross is getting his hand up like crazy. He's waving, doing jumping jacks there.
oh, yeah, I was going to say, David, when I was looking at this the first time, I thought this was clearly something which some, ultra product filter or whatever would be able to deal with more easily.
Yeah, well, that I don't know. And the reason it looks like I'm asking like crazy is my hand is like right in front of the webcam here. No, it's possible. There are some clever ways of constructing non-measurable sets by decomposing the interval using ultra filters, but they're equivalent to stuff you can do with non-standard analysis, like taking infinite decimal representations of numbers and taking all the ones whose hth digit is 7, where h is an infinite integer. That's a non-measurable set. But anyway, that's not what I wanted to ask. There was a monograph. Sierpinski gave some lectures in India in the 1950s, and they were collected into a monograph, which the AMS published in like 1958, 1959. And unfortunately, I'm at home, so I couldn't reach behind me and find it. And even though it was in the office, I think it's buried under a mountain of books right now. But I was curious whether, because the book is a compendium of this kind of results.
Yeah, so I saw a reference to it, and I saw also that it was reprinted by Dover Publications around 1950, 51. But
well, the AMS actually had a series, and the AMS published a monograph which included that one. It included something by Klein. It was four different monographs by four different, but that was one of them.
yeah, so I had meant if I had gone to the Graduate Center today to look in the library to see if it were there, but since I never leave my house.
If you haven't seen it before, I warn you that if you pick this thing up and start to read it, you will lose a chunk of your life, because it's beautifully written, and it just contains one neat result after another of this kind of variety.
Yeah.
But I was just curious whether you knew offhand whether this particular result.
No, I haven't seen it. I know that there is still a lot of work being done on these finite decomposition of spheres. And there's actually even a paper by one of our colleagues, Dennis Sullivan, with Pierre Deline, on decomposing a sphere into pieces. But this uses a little bit more than the baby stuff I was talking about today. But I did think it was interesting that Deline and Sullivan at some point were interested in this, and enough to write a paper on it.
Mel,
Yes.
do you know this book?
No. Who's the author? I can't read it.
Hugo
Can you show
Steinhaus.
us?
Right?
Steinhaus.
Steinhaus.
Yeah, there are many more problems here.
Well,
Oh,
Look,
this is in
look at
Polish?
this.
Oh, I
Look
was
at
like watching
this.
TV. I didn't want them to hear me.
yeah.
Yeah.
Excuse me,
Sorry,
is this
sorry.
book in Polish?
Yes,
Okay.
in good Polish.
Now, I cannot see, I can see only matematyczny, but the first word is
Kaleidoscope.
Yeah, kaleidoscope. Yeah,
kaleidoscope. Oh,
mathematical kaleidoscope.
and who is the author?
Hugo Steinhaus,
Oh, Steinhaus.
the hero of today's talk.
Yeah.
Oh.
So
Is
evidently,
is it possible to get this book somehow?
I don't know. My wife found it between books in old shelves just a few days ago. I even don't know where it came. I mean, how I got that. This is I didn't read it, you know. but there are lots of problems like this, you know, over there.
Yeah, yeah, yeah. I
Sitting
know
at Polish
Steinhaus.
school, right?
Yeah, yeah, yeah.
Yeah, okay.
No, he has a book that's been translated to English, 100 Problems in Elementary Mathematics.
Yeah.
I
don't know
wonder
if
if
that-
this has something in common. I mean, there is the title is different.
I mean,
Yeah.
the one that everybody knows in English is Mathematical Snapshots, but
Right.
that would be different from this. It
Yeah.
has no problem.
But
So-
the Steinhaus problem that Mel was talking today is not in the book.
Yeah, and as I said, I don't know if he ever published it. It was in this paper by Morzikevich, but he said this is a problem of Steinhaus. So I had read somewhere that Steinhaus somehow managed to survive in Poland under the German occupation by teaching mathematics secretly to people.
Really? Oh, I didn't know
And
that.
that somehow he was in that way responsible for keeping alive the Polish mathematical school, notwithstanding all the people who either emigrated or were killed.
Which period you are talking about, Mel?
Sorry,
Which period you are talking
during
about?
World War II, during the German occupation.
Okay, yeah.
Uh,
I was fortunate to meet him once personally when I was very, very little kid.
yeah.
He also wrote a nice, beautiful limericks or a little bit, you know, how to say, I would say limericks, yeah. Yeah, just he was easygoing fellow, writing things and talking about mathematics for general public. Besides, of course, his very good research work from, you know, from Lvov, right? Period. Yeah. You know his best mathematical achievement, right?
What?
Banach Steinhaus?
Yeah, exactly. Yeah, but also, yeah, I think he used to say that his best achievement was Stefan Banach.
Was he Banach's teacher?
No, Banach was a little young man sitting on a bench somewhere talking
Oh,
to
yes.
Nicodim and Steinhaus was passing by and he heard the word Lebesgue measure. That was really shocking for him. So he stopped and asked the names, and that's how it started. Yeah. There is no alcohol involved.
Mel, I gotta ask a question that may be out of context, but the result that you mentioned by Sullivan and the lineage, I'm wondering what would follow from your result in 2 dimensions and the fact that the sphere in spherical coordinates, you can basically parameterize the points by points on a square, by altitude and by latitude. And so I'm wondering, I mean, you parameterize the sphere by the points on the square, and then you perform the 2-dimensional construction on the square. And I'm wondering where that implies what Sullivan and the lineage did. I mean, I haven't seen this decomposition, but I mean,
Yeah,
this
I
out of
think they were
context,
looking at higher dimensional spheres, but I can send you their paper.
I'd be glad to. I mean, it's the situation like on the circle.
Right.
I mean, the circle looks like the image of an interval. So the things that you do in the interval, so there is a corresponding statement for
Yeah.
the circle. So, but I would be interested in seeing, yeah. All right, thanks.
But as you might guess, they use a non-trivial bit of number theory or arithmetic geometry kind of stuff in what they're doing. It's not just, you know, it's not the mathematics of the 1920s.
Mel,
Other questions or comments?
a question. Mel,
Go ahead.
you know Jan Michalski personally, right?
Who?
Jan Michalski.
I know him by name. I do not think I've ever met him.
Okay, he's old man now, but
Yes, he is.
yeah, he's one of those Polish folks.
Yeah.
He's
Remember earlier
like
in
a
the year,
logic
last year, I talked about a problem he submitted to the monthly. And
So you said that his proof is more complicated than von Neumann?
oh, his yes, I think so. Yes.
Do you have guts to tell him?
Sorry?
To have guts to tell him?
I would have no hesitation to tell him, but
Yeah.
you know, he wrote, his paper goes back to the 1950s, the one the one that was referred to. And 1957, in fact. So, and he had written several papers on these finite decompositions of geometrical objects, intervals, spheres, circles, and so forth. But he was looking at, but these are really papers in set theory, because he's decomposing things into infinite cardinals greater than Aleph naught. But like what's sort of strange to me, who's not a set theory guy at all, is that he proves a theorem for cardinal numbers between Aleph naught and 2 to the Aleph naught. And we used to think that there was no cardinal number between Aleph naught and 2 to the Aleph naught. So, and it has to be strictly less than 2 to the Aleph naught, because you can decompose anything into singletons, anything that's, like any interval. So it has to be a cardinal number strictly between Aleph naught and 2 to the Aleph naught. And
he demolished Paul Cohen?
right? Oh, certainly, yeah, long before Paul Cohen. Yeah, and it's like
I mean,
1950s. And Paul
You can
Cohen was something-
assume,
yeah,
you can assume that such cardinals exist and work with that, right?
you can, but
You pick your axioms here.
yeah, but why?
You get interesting mathematics.
Yeah,
Yeah, there's a natural axiom in the theory of infinite games, which implies that there's exactly one cardinal between Aleph 0 and 2 to the Aleph 0. Some natural axiom.
by the way, there's a paper in an article in the current issue of the Notices on quantum coin flipping. And I could not understand the first paragraph or two. So if anyone ever can figure it out, I'd be curious to know.
By the way, there is a paper related to that in your talk. There's a paper in the monthly, maybe 20 years ago, on getting a measurable set from coin flipping, a non-measurable set rather from coin flipping. Which I don't remember the author or the exact reference, but I remember once teaching our graduate measure theory class and having the students work through that paper.
You have to have a lot of coins to do it.
Yeah, of course. or a very strong thumb.
Okay, everyone, have a enjoyable Thanksgiving.
Yeah. Yeah.
Everybody eat your turkey.
No, I prefer duck.
Duck.
Yeah.
Well, okay.
That's a little detour.
Yeah. I prefer turkey, even though both of my kids are vegetarians. So we have to have a turkey plus a fish. Fortunately, they're pescatarian, so they will eat fish, but they won't eat meat. Makes it very complicated. So anyway, hopefully we'll all be back in 2 weeks.
All right.
Be well all.
Happy Thanksgiving.